Saxon Algebra 2, Lesson 92, Boat in the River Problems. Yay, I love these students. They're not too hard, and they have a great storyline that goes with them. They are variations on our old friends, the dirt problems, though most students find these much easier because there aren't so many different ways that the story can take place. It's pretty straightforward when you have a boat in the river problem. Now, here's the thing about boats and rivers. I'm assuming that you have done at least a little bit of boating, even if it means, taking a ferry. But you know that when you ride in a boat, there are actually two rates, right? There's not just one rate like the rate of the car. There's the rate of the boat that you're traveling in. It's usually propelled by a motor or an engine of some sort, or human power, right, if you're paddling, or even the power of the wind if you're sailing, although we're not really going to mess with that one too much. And then there's the speed of the water, which is sometimes called the current. As you know, if you have ever powered a boat on your own, this can make a huge amount of difference, because if you're going with the current, say on a river, you sail along nicely because you're moving with the river, right? That's called going downstream. And if you're paddling against the direction of the water, if you're paddling upstream is what we call it, then it's far more difficult, right? Because you're fighting your boat, the speed of your boat is fighting the speed of the water. This is the story of our good friends Lewis and Clark, who left St. Louis, Missouri, hoping to find a water route to the Pacific. Oh my gosh, I love Lewis and Clark. I'm obsessed with Lewis and Clark. I do have a favorite of the two of them, William Clark, all the way, was my fave of the two of them. No one in their expedition died. They've achieved their objective of finding the Pacific coast. They made friends with the Indians. They brought back tons of information about new species of plants and animals. They're just all around gems. Plus, the expedition was under the supervision of my favorite president, Thomas Jefferson. Pardon me, I got so excited about talking about TJ that I couldn't talk. When my daughters were students, I taught a class about the presidents, where we studied all the presidents, and I obsessed on and on about why I think Thomas Jefferson is so fabulous. I'll spare you. But Lewis and Clark, I will not, because here's the thing. When Lewis and Clark left St. Louis and traveled up the Missouri River, they were traveling upstream. And when they finally, they thought they would be able to just jump from one river to the next. It didn't work out like that. They had to portage through the mountains forever. But eventually they found the Columbia River, and they jumped in with their boats and just paddled, and the current just swept them all the way to Astoria on the Pacific coast. So they illustrate this perfectly. I want to talk about the downstream equation first, which was second in their journey, but it's the easier one to understand. This is when they hit the Columbia River, right? And they were traveling with the current. What happens there is, I'm going to rewrite this in the form of rate times time equals distance. I'm just flipping it around. The rate has two pieces, the rate of the boat plus the rate of the water, times the time downstream equals the distance downstream. What we're recognizing here is that the boat and the water work together when we're traveling downstream. And that was Lewis and Clark on the Columbia. Whoosh! They just shot right the heck out to the Pacific coast because they were going with the current, the speed of the water. All right, now we backtrack. They're leaving St. Louis, Missouri, and they're taking the Missouri River up into the mountains, right? They're climbing up to the high part of the continent. So here, I'm sorry, I have to write upstream. I got so excited. Upstream equation and this is the Missouri River part of it. Here, the speed of the boat is lessened by the speed of the water, right? So if you aren't working at least as hard as the water's pushing against your boat, you're gonna go backwards. You have to be faster than the water. You multiply that by the time upstream, and that equals the distance upstream, all right? These are our two formulas. With these in our hand, we are gonna be just fine with these problems. They're fairly easy to use, and as you know, you've already been practicing the mechanics of that. 1, 2, 3 example problems. Ready? Let's go. We're gonna need these. All right, example 92.1. Robert and Clay could go 60 miles downstream in the same time it took them to go 20 miles upstream. Okay, before I even did that, what I wish I would have done is reminded you, it really helps if we do this. Just lay out all the variables. I'll scooch up a little bit so you can see better. The speed of the boat, the speed of the water, time downstream, distance downstream, time upstream's distance upstream. The distances aren't always the same, the times aren't always the same. So we just want to set up for everything. The speed of the boat and the speed of the water will be the same in both scenarios. So we don't have to worry about that changing. Okay, they could go 60 miles downstream. Okay, that's the distance downstream. In the same time it took them to go 20 miles upstream. So the distance upstream is 20. And the times they said are the same, so I'm gonna rewrite both of them as just a plain T. If the times are the same, if anything's the same, you can drop the subscript and just let it be the same. John's not telling us what the time is, but he's saying, psst, it's the same. If the speed of their boat was 8 miles per hour in still water. Now when John uses that language, he's just saying that's the speed of the boat, not the speed of the water. The speed of the boat alone is 8 miles per hour. What was the speed of the current? Current equals the water. Same difference. What was the speed of the current and what were their times? Okay, so we're solving for this and the times. Do we have enough information? Let's find out. We have to set up two equations and solve them as a system. So let's start with the downstream. Oh, I'm sorry. I'm trying to copy the empty brackets. B plus W times TD equals DD. Okay, so this will be the downstream equation. This will be the upstream equation. We have a minus there instead of a plus. And then these values could be different. Okay, downstream equation. So I'm working from here. Speed of the boat is 8. Speed of the water, we don't know. Time downstream is just TD. And the distance downstream is 60. Upstream, the boat is 8. The water, we don't know, so we just put in W. The time upstream is just T, and then the distance upstream is 20. There's our system, okay? I put the letters here just so I would know which one of these to copy. Now we don't really need these anymore. All right, I'm gonna distribute top and bottom, and I'm gonna get 8T on the top plus TW equals 60. And now I'm going to get 8T minus TW equals 20. Okay, that's just cleaning that up and writing it in a more civilized format. All right. Now, look, these already canceled. 16T equals 80. Divide by 16, and I'm quite sure that T equals 5 hours is our unit. Yay! It worked. This one was super easy, right? We didn't have to do anything fancy. Now we're gonna have to use one of our equations to solve for speed of the water. We can use either one. Let's just use the top one. So I'm going to copy that. Oh, I will copy it from here because it's got most of the things filled in. So it's 8 plus, and then W we don't know yet, so we'll just put W, times the time, which is 5, equals 60. Now I distribute. 40 plus 5W equals 60. Subtract the 40. 5W equals 20. So the speed of the water is 4 miles per hour. I get the units just out of the story. There's nothing magical about that. All right, so John asked us, what was the speed of the current? Water and current are the same thing, so it's 4 miles per hour. And what were their times? It took them 5 hours both times. Make sense? Yay. Okay, let's try another one. And again, these are like the distance problems in that John can fool around with which variables he gives us, but the equations are always the same. We don't have to choose between the 3 different pictures, right? All right, 92.2. Okay. The steamboat, oh, let's write down our equations. Oh, I better because I don't have them. The downstream equation is where we add them. And we remember this is the rate. So, and then we multiply it by the time and that equals the distance. And then upstream, that's when we have to subtract. This is the Missouri River. Oh, poor Lewis and Clark. Killing their arms. Their biceps must have been enormous trying to get up that freaking Missouri River in their canoes laden with all their supplies and their dog. Okay, now we make the list of all the variables we need. Boat, water, time downstream, distance downstream, time upstream, distance upstream. I write them in the same order that they make their appearance in our formulas, just like in a movie. You know how they list the cast in the order of appearance? That way, when we go to plug these into this, it'll be semi-organized. All right, now we're gonna read the story and try to fill in the numbers. The steamboat, Juby Fountain, could go 70 miles downstream, that's a distance, in 5 hours, that's a time, but required 6 hours to go 48 miles upstream. So 6 hours for 48 miles upstream. What was the speed of the boat in still water, and what was the speed of the current? So we don't get either of those. All right, that seems really hard, doesn't it? But we can do it. Okay, so B plus W is gonna stay the same for both of these. Time downstream is 5 equals 70. See, I'm just plugging in. And then B minus W times 6 equals 48. Okay, I just plugged in as best I could. Now, we shall need to distribute, won't we? Both equations. 5b plus 5w equals 70. 6b plus minus 6w equals 48. All right. We're going to have to change one of those, aren't we? In order to get these to eliminate. That's our best bet for these. We don't want to fool around with substitution. But I say let's work on canceling the w's. I mean, it's kind of the same, but these have the opposite signs. So we'll multiply the top one by 6 and the bottom one by 5. Ready? Grace is having puppy dreams. 30b plus 30w equals 420. And 30b minus 30w equals 48 times 50 is 200 plus 40. Right? I did 5 times 4, that's 20, but it's actually 40, so it becomes 200. And then 5 times 8 is 40. 200 plus 40. That's how I did that. All right. We now have a beautiful eliminatable pair of equations. And we get 60b equals 660, John, divide by 60. And we get that B equals 11, right? 660 divided by 60 would be 11. That's the speed of the boat, and we're measuring it in miles per hour. We know that boats don't always, sailing vessels don't always use miles per hour. They have a different system, but John just uses miles per hour to make our life easy. Okay, now we need to solve for the rate of the water. We'll just pick one of these, nice and easy. So now we'll do 11 plus W times 5 equals 70. 55 plus 5W equals 70. Subtract the 55. W equals 15. So the speed of the water equals 3 miles per hour. Beautiful. They have a bunch of strong dudes rowing this canoe, so they were able to totally thrash the current as they were going upstream. Make sense? Okay, good. The equations that we were practicing solving were kind of harder than this, weren't they? These have been pretty straightforward. Let's try one more. Example 92.3. I'm going to try and squeeze it in on the bottom. What can I say? All right, let's make our list of variables. Boat, water, time downstream, distance downstream, time upstream, distance upstream. I'm getting squishy. I hope you can see. There, I bumped it up so it's easier to see. Hopefully. We did all of that. As soon as I saw it was a boat in the water problem, we just went right to this. And we don't even have to draw pictures. We've got our formulas right handy, right? They're easier than the Lord of the Rings and Princess Bride type problems. All right. The water in the Flint River. Oh, it's a story from Michigan. I live not too far from Flint. Not close, but not too far. It flows, the water flows at 5 kilometers per hour. Okay, that's the speed of the water. A speedboat can go 15 kilometers upstream, that's a distance, in the same time, let's make it plain T, it takes to go 25 kilometers, sorry, not millimeters, that'd be a very short trip, 25 kilometers downstream. How fast can the boat go in still water? That's just code for what's the speed of the boat, all right? In still water just means we're not counting the water, we're just counting the boat. That seems so complicated, but it's really straightforward. All right, there we've got everything we need. There's our formulas. First we'll have the downstream, and then we'll have the upstream. The difference is the minus. Right? Okay. The boat we don't know, so we'll put B's in there. The water is 5. The time is the same for both of them. And then the distance downstream is 25 and the distance upstream is 15. If it helps you just to keep it all straight, to put downstream and upstream by them, that's a good idea. I just remember we always do downstream first because that's the plus one, that's the easier one. And for Lewis and Clark, that was the Columbia. They had to wait till the end of their trip to be like, whee! In the beginning of the trip, they were like sweating and swearing, I'm sure. All right, now we're just gonna clean up these equations and see what we've got. BT plus 5T equals 25. BT minus 5T equals 15. Now, here's the thing. Watch this. We could let these cancel. They want to cancel so badly. 2bt equals 40. And we could divide it by 2, right? And then we can say that bt equals 20. This is the kind we practiced, right? This doesn't give us one of our answer because it's two variables together. But what we can do is pick one of these two original equations, plug the bt in for 20, and then solve it for t. Let's use this one because it's plus. That's easier. So now we say 20 plus 5t equals 25. See what I did? I just plugged bt in right here for bt. So 20 plus 5t equals 25. Subtract the 20. 5t equals 5. Divide by 5. And then we get that the time equals 1, right? And now we can go back to this and say, okay, if b times t equals 20 and t equals 1, then b must equal 20. Make sense? That is one way to do this problem, and these are indeed the correct answers. I mean, technically, we only need these two. We don't need that. Okay? Excuse me, I'm yawning. That worked out perfectly well, and that was glorious and perfect. However, what we could have done way back here, when we saw that canceling this out was going to get us a double variable solution, we could have said, we don't want to do that. That's gross. We don't want to. What we could have done is said, okay, let's take these two equations, bt plus 5t equals 25, bt minus 5t equals 15. We could have said, hey, let's resist the temptation to just use this. Let's multiply this whole thing by -1, and let's eliminate this row. Okay? It would have been a little bit more work, but look what would have happened. We would have changed this into minus bt plus 5t equals minus 15, right? Flip the signs on all that. Draw a line through that so we don't get confused. That goes away. 5t plus 5t is 10t. 25 minus 15 is 10. And right there, we could have gotten to the answer quicker, that t was equal to 1, and then we could have just plugged in and solved. Either way is fine. When you see that you're setting yourself up to have a double variable solution, it's okay. You can usually keep going and pull those, tease those apart and get the values for both of them. But if you want, you can say, no, I don't want to do the double variable thing. I choose to eliminate I want to eliminate the double variable and keep just the single letter and solve it that way. All right, so you have options. That is the end of lesson 92, Boat in the River Problems, Lewis and Clark. I didn't even mention Sacagawea, and I feel very strongly about her as well. I am very glad that we could have this moment in history together. I will see you on the FaceTimers or the Messenger video chat, whichever platform you prefer. But I will chat with you hopefully soon if I haven't already. Thank you, goodbye.